Okay, so in the previous class, we were looking at some basics of probability, essentially just a recap. And we'll continue to do so today. You may see some concepts that you've not seen before. So we'll recap some of the basics of probability and also some elementary concepts of convex sets and functions. All right, we'll keep reusing some of these tools later on in the course. So the lecture notes will contain all of this. Another point is that I will perhaps not give separate problem sets, but the lecture notes will contain a bunch of problems in between. So you can use those you can try to work those out. But you can also go through some of the problems in the reference textbooks, particularly the book by Cover and Thomas, which is the first reference. All right. Okay, so let's continue. So towards the end of last class, we looked at some of these so-called concentration inequalities, which essentially tells you what is the probability that a particular random variable deviates from the mean by a certain amount. And two such important concentration inequalities are the Chebyshev inequality and the Chernoff bound. While the Chernoff bound is very generic, it's not always easy to use. So we'll use a simplified version of the Chernoff bound, particularly for Bernoulli random variables. And we'll see that this is sufficient for most of our purposes. All right. So for Bernoulli random variables, in particular, suppose that x1 through xn is a sequence of random variables which are all independent of each other and all Bernoulli. For some p between 0 and 1. All right. So we know that as n becomes large, what would you expect 1 by n summation xi to look like? Which is p. All right. So it would be close to p. So the Chernoff bound allows us to deviate. What is the probability with which it deviates from p? Right. So the probability that the quantity 1 over n summation I equal to 1 to n xi minus p deviates by an amount epsilon. All right. This is less than or equal to 2 times, or let me explicitly mention both bounds. So let's look at one of the tail bounds. So what is the probability that the empirical average of the xi's is greater than p by an amount of epsilon? All right, that's what I'm asking for. Let me say that not just epsilon, but say epsilon times p. All right. So this probability is less than or equal to e to the power epsilon divided by 1 plus epsilon whole raised to 1 plus epsilon whole to the power n times p. All right. This is something that you can get essentially by taking the Chernoff bound and trying to minimize the right hand side over all possibility. Remember that the Chernoff bound is parameterized by a t which is greater than 0. So for every value of t greater than 0, you get a bound on the right hand side. And obviously, since it holds true for all t greater than 0, it also holds true for, you can take the minimum over all possible t on the right hand side. And doing so would get you something like this. We can further simplify this to a form that is more useful. So this is less than or equal to e to the power minus epsilon square n times p divided by 3. But the last inequality holds true only for epsilon between 0 and 1. And for the other tail, again you can prove an identical bound, summation I equal to 1 to n, summation xi minus p less than or equal to minus epsilon times p. This is also less than or equal to e to the power minus epsilon square np by 3. All right. We'll not prove this right now. It's essentially just manipulation of parameters and just some simple calculus. The lecture notes contain a sketch of how you would derive these particular bounds.
The first one is the upper bound.
Both of them are upper bounds, right? But they're bounds on two different quantities. One is, both of these are upper bounds on the probability.
Inner event. Probability.
Correct. So the event is, this is what is called the right tail.
Yeah. So it's
Right.
less than
Correct. It's less than or equal. Which one?
first one.
So this is the probability that the average, that the empirical average is greater than or equal to p plus epsilon times p. Right? And this is that the empirical average is less than or equal to p minus epsilon times p.
This is the modulus exactly.
I'm sorry?
Yes, the modulus of this is greater than epsilon times p.
That's true. But these are two events. So let's see visually what this represents. I have the real line and this is my p, right? I'm interested in the random variable y, which is equal to 1 over n summation I equal to 1 to n xi. Correct? Now with high probability, I would expect this quantity y, as n becomes large, I would expect this quantity to lie somewhere in a neighborhood of p. Correct? And what you may be more familiar with, and what, for example, the Chebyshev inequality asks, is what is the probability that it deviates from p by an amount epsilon, right, on either side. So this would be p plus epsilon times p, and this quantity is p minus epsilon times p. Correct? What I've written above are two things. One is this particular probability that it is greater than p plus epsilon times p. Right? The second probability is the probability that this is less than p minus epsilon times p. Correct? Is that fine so far? Great. So now if I'm interested in the event or the probability that mod 1 by n summation I equal to 1 to n xi, which is my y, minus p is greater than epsilon times p. Can we use the bounds above to get a bound on this? If so, how? Yeah? And why can I just add them up? Correct. So this the event over here that y is either greater than p plus epsilon times p or less than minus epsilon times p. It's a union of the events given by these two, and therefore I can use the union bound and say that the probability that mod y minus p is greater than epsilon times p is less than or equal to 2 times e to the power minus epsilon square np by 3. Right? And this holds true only for epsilon being between 0 and 1. But that suffices for what we want to do. All right? Note that this is only a bound, it's not the exact probability itself, and in many regimes this can be a pretty weak upper bound. But that's okay, because in most cases what we'll be interested in is to show that as n tends to infinity, the right hand side tends to 0. And in particular, the right hand side tends to 0 exponentially fast. That's enough, for at least for the purposes of this course. All right? Any questions so far? Okay. So this is one very important tool that we'll frequently use. Another simple but very useful trick that we'll use is something to do with indicator random variables. All right. So suppose we have an event E. Let E be an event. All right. The indicator random variable corresponding to this event E which will denote one subscript E it's another random variable which is a function of this particular event. It takes the value 1 if E occurs and 0 otherwise. Okay, it's something very simple, nothing fancy. The usefulness of this indicator random variable is that expectation of the indicator random variable, what is that equal to? It's equal to the probability that the event occurs. Right? So it's simply the probability of E times 1 plus the probability of E complement times 0, which is simply the probability of E.
But this is simply a Bernoulli random variable.
It's a Bernoulli random variable, yes, exactly. It seems very simple, and you're probably wondering why I'm even making this point. But let's see how this trick can be used. Okay. Now, what I want to do is, let's suppose that I have some set. Okay. So let's say that X is a finite set. All right, and X be some random variable which is distributed according to a probability mass function P subscript X. And X can take values from this particular set. Okay. Again, I'll be using this notation X tilde Px to denote that X is distributed according to the probability law Px. Let's suppose that A is some symbol from this set X, script X. All right. Now what I want to do is find what is the frequency. I want to say something about the frequency of occurrence of a particular symbol A if I observe a sequence of random variables drawn according to Px. All right. So suppose that x1 through xn are independent and identically distributed according to the law Px, and so at the same time I'm also introducing some notation that I'll be using. So any vector or sequence of n random variables, I'll denote this x superscript n. Okay. Sometimes I'll just use x with an underline to indicate that this is a vector or a sequence of random variables. I'll use this underline when I don't particularly care about what is the length of the sequence or the length of this vector. But in most cases, I'll use this particular notation x superscript n. Okay. So I have n IID random variables all drawn according to Px, and each symbol comes from this set script x. I want to know how many times does A occur in this particular sequence. Okay. So let me also introduce a notation for this. Let me say that eta subscript A of xn is the number of times A occurs in the sequence xn. Okay, that's simple enough, at least simple enough to visualize. But so firstly, what I want to know is what is the expected number of times the symbol A would occur in xn. What would you expect this to be? What would be your guess? You would guess that this should be n times Px of A. Correct? Because each symbol is IID A. But how do we prove this? The simple trick is to use indicator random variables. Right? So eta A of xn is the number of times A occurs in the sequence xn. I can write this as summation I equal to 1 to n indicator xi is equal to A. Right? So I'm counting a 1 every time xi is equal to A and a 0 if it is not equal to A. Correct? You can very easily convince yourself that this quantity inside the parenthesis is exactly eta A of xn. Right? Now, why is this particularly helpful? This is helpful because now I can use linearity of expectation. Right? I can take the expectation inside the sum, and this is simply equal to summation I equal to 1 to n expectation of indicator that xi is equal to A. Right? Which is simply equal to summation I equal to 1 to n. The expectation of the indicator is the probability of the event, which is the probability that xi is equal to A, which is Px of A. And this is simply n times Px of A. Right? Any questions so far? Okay, great. So this is fairly straightforward, but let's go back, revisit the steps that we have done and see if this particular statement holds in more generality, right? Now, in these steps, I never really made use of the fact that the symbols are independent of each other. I just required identical distributions. So even if the xi's are all dependent, strongly dependent in fact, this expectation is still equal to n times px of a. So as long as the xi's are identically distributed, they need not be independent. As long as they're identically distributed, the expected number of times the symbol a occurs in the sequence is equal to n times px of a. All right? Which using this, there are other ways you could possibly do this, using some kind of counting arguments perhaps. But this formalism using indicator functions makes it very easy to do such calculations. All right? Okay, since we've anyway done this exercise, what is the probability that the number of times you see a deviates from n times px of a by a certain amount? Right? Minus is greater than or equal to, let's say, n times px of a times epsilon. Yep, 2 times e to the power minus epsilon square n times there's also px of a divided by 3. Right? Okay, so that's fine. Let's do another exercise, which is going to be just a simple extension of this. What is the probability that eta a of xn minus n times px of a? So this is what we've done is this for fixed a, right? Any questions? Is that okay? Any questions? Okay. Right. So what is the probability that the number of times any symbol occurs, not just one particular a, the probability that this is greater than n times px of a times epsilon for any a from this particular set, script x. So for example, let's suppose that the symbols are 0, 1, 2, 3. The set script x contains 0, 1, 2, or 3. What is the probability that, effectively what I want to know is what is the probability that the number of times 0 occurs is close to px of 0, and 1 occurs is close to 1, and 2 occurs is close to px of 2, and so on, right? Or essentially, what is the complement? What is the probability that any one of the symbols deviates from its expected value by an amount n times the probability times epsilon? Correct. So what is this probability? How can we upper bound this particular probability? Again, very simple, straightforward. You just use a union bound. All right? So this is less than or equal to summation overall A coming from the set X 2 times e to the power minus epsilon times epsilon square n times px of A divided by 3, right? Again, minor point to note is that epsilon should be sufficiently small for this to hold, should be less than 1. Now, usually summations, we want to simplify such quantities as much as possible. Since this is less than or equal to the size of x times the largest of those terms in the summation, right? So I can write this as less than or equal to size of x times max overall A in x e to the power minus epsilon square n times px of A divided by 3, but this is also equal to 2 times size of x e to the power minus n epsilon square times the smallest probability p min divided by 3, right? Because the A that maximizes this quantity is the one that minimizes this particular quantity, right? Because I have e to the power minus a function of A. Okay. Any questions so far? Okay. So this basically tells you that if you see a sequence of IID trials, then every symbol, the empirical frequency of every symbol is going to be close to its expected value. It's equal to its probability with an overwhelming probability, right? The probability that this deviation is large, in fact, decays exponentially in the number of trials. All right, that's a very powerful statement. This holds true for IID sequences, but may or may not hold true if there's some amount of dependence. All right, and we'll make use of. We'll also analyze probabilities where we don't have dependence. We don't necessarily have dependence among random variables. So, what is the sequence of IID random variables? When do you say that x1 through xn are IID? How do you formally state, or how do you define a sequence of random variables to be IID? Is pairwise independence enough?
Probability of for all I, probability of xi given all x1 to xn not including xi
Okay.
is equal to probability of xi.
Okay. That's one way of probability of xi, but something more. It should follow the same distribution px. Right. So that's one way of saying it. That is, conditional probability of any xi given x1 up to xi minus 1 and xi plus 1 up to xn of xi given this is equal to px of xi. Right? And this holds true for all I and all xn. Correct? That's one way of stating it. The other way is that the joint distribution of x1 through xn is equal to the product of the marginal distributions, and all the marginal distributions should follow the law Px. So this is product I equal to 1 to n Px of xi, and this should hold true for all xn. This is something that should hold true for discrete random variables. For continuous random variables, you just replace the PMF with perhaps the PDF. All right. Mostly we will assume that all continuous distributions have a valid PDF. That's a basic assumption that we will make in this particular course. But note that in general this may not hold. All right. Okay. Now we want to extend this definition to have some notion of dependence, right? What is the minimal amount of dependence that you can have in a sequence of random variables? So one way of having this dependence is to say that each xi depends only on xi minus 1 and not on the remaining, on the previous xi's, previous xj's, right? So given xi minus 1, xi is independent of everything else that happened in the past. Okay? So first order Markov chain with initial distribution Px and transition kernel, sometimes called the transition probability law, P x prime given x is one where the joint distribution Pxn is equal to Px of x1 times the product I equal to 2 to n Pxi given xi minus 1 of xi, or I should say Px prime given x of xi given xi minus 1. All right. So a simple first order Markov chain is where you're adding independent increments at each round. So let's say that suppose that x1 through xn are all IID. All right, these are IID random variables, and let me define yi to be summation j equal to 1 to I of xi. All right, so all of these partial sums. All right. Then the random variables y1, y2 up to yn form a first order Markov chain. and I'll leave this as an exercise for this. So first prove that this is a first order Markov chain. And find the initial distribution and the transition kernel. Any questions? Okay. Just as we defined a first order Markov chain, we can define a kth order Markov chain, where each xi can depend only on k previous symbols. All right, so p xn is equal to p xk of xk times product I equal to k plus 1 up to n of xk of xi plus 1 given or pxi given x I minus k up to x I minus 1. All right. Now, one of the main reasons why I'm defining these kth order Markov chains is that language can be very well approximated by a kth order Markov chain. All right. So, for example, if you take English text, a standard piece of English text will not have very long range dependencies. All right. I'm saying this rather loosely, but as we'll see, in certain contexts, particularly when we come to compression, if we treat English text as a kth order Markov chain, then we get excellent results. All right. And there are other statistical analyses that have been done on English text, which in fact suggest that it can be very well approximated by a kth order Markov chain. So did anybody try the exercise I gave in the previous class? I asked you to take some English text file, compress it, and try to find the compression ratio.
1.05 to 1.2, the range I put.
What do you mean 1.05?
Compression ratio 1.05 to 1.2, the range.
Are you sure? Because the compression ratio should be less than 1. Right? The size of the compressed file should be smaller than the size of the original file.
Maybe I have done
The other way around. Okay. So what you should get is roughly in the range of, depending on the size of the file, something around 0.25 to 0.3. Right? And it doesn't matter which file you take. You can take War and Peace, you can take Harry Potter, you should get roughly the same compression ratio. Right? And it shouldn't even significantly matter whether you use zip or gzip or any other compression utility. Some of these are slightly more optimized, so there may be minor differences in the compression ratio that you get, but by and large it's going to be the same. All right. And in fact, in the second half of the course, we'll see some of the algorithms used for compression. And one of the compression algorithms that we see will be the main component of what is used in pretty much all of the compressors that you see, whether it's zip or gzip or 7-zip or anything else. They only differ in minor implementational improvements. All right. Okay. Okay, so continuing with this, so the lecture notes contain some more basics of probability that will probably skip for now. We'll use them only a little bit in the course, but please do go through the notes in detail. All right. So now we'll talk a little bit about convex sets and convex functions. So what is a convex set? So a set A, which is a subset of, let's say, R to the n, what is the definition of convexity that you've seen?
X1, X2 belongs to A, then any convex combination.
Correct. It's convex if for all x1, x2 in the set A. So you have some set, you take any 2 points, the straight line joining these 2 points should also belong to the set. All right. What I've drawn over here is not a picture of a convex set, because I can take 2 points over here and draw a line which lies outside the set. Alpha x1 plus 1 minus alpha x2 belongs to the set A. All right. And this combination, any combination of the form alpha x1 plus 1 minus alpha times x2 for alpha ranging between 0 and 1, that's called a convex combination. Geometrically, this represents the straight line joining these 2 points, or the line segment that joins these 2 points. All right, so similarly, if I have a function that is defined on a convex set, so I have some function which is defined maybe over a subset of Rn. It need not be defined over all of Rn. So the function is convex if f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha times f of x1 plus 1 minus alpha f of x2. All right, and what does this mean geometrically? Right. So if you had to visualize what a convex function is, what would it look like?
Multiple line segments.
Right. Yeah. So it would look something like a bowl, right? So this, if you had to draw a generic convex function, it would look something like this. So if you take any 2 points, let's say I take x1 and x2, this point here is f of x1, x1 comma f of x1. This point here is x2 comma f of x2. The set alpha f of x1 plus 1 minus alpha f of x2, that would essentially correspond to this line segment that joins f of x1 and 1 minus f of x1 and f of x2. Right? So any point over here corresponds to alpha x1 plus 1 minus alpha x2, comma alpha f of x1 plus 1 minus alpha f of x2. Right? As I vary alpha from 0 to 1, I get this line segment that joins these 2 points. Right? Is that okay? Any questions? Great. But f of alpha x1 plus 1 minus alpha x2 would essentially be a point along this curve. And the function is convex if the curve always lies below this line segment. All right? I'm sorry? Okay, great. So let me take a function. All right, take any 2 points, x1 and x2. What does this point correspond to? The xy values. This is x1 comma f of x1. Right? And this point is x2 f of x2. Now for any alpha between 0 and 1, what does the point alpha x1 plus 1 minus alpha x2, comma alpha f of x1 plus 1 minus alpha f of x2, what does this correspond to? Where would this lie? So remember that the x value is basically alpha x1 plus 1 minus alpha x2. The y value is alpha f of x1 plus 1 minus alpha f of x2. So as I vary alpha from 0 to 1, what kind of a curve would this represent? It would be a straight line or a line segment. Right? So this is basically this line segment that joins these 2 points. Correct? So for the same range of alpha, let's consider alpha x1 plus 1 minus alpha x2, comma f of alpha x1 plus 1 minus alpha x2. What does this correspond to? A point on the curve, right? A point on the curve evaluated at alpha x1 plus 1 minus alpha x2, which is precisely this. And the definition and the function is convex if this line segment joining any 2 points on the curve is going to always lie above the curve. All right? Which is now intuitive. Once you see the definition, this is natural because that is precisely what it means to be a bowl-like function. Right? Any questions so far? Okay. So this is what it means for a function to be convex. We'll say that the function is concave if minus f is convex. So just one definition is sufficient. I don't need to give a separate new definition for concavity. There's also a minor point. The function is said to be strictly convex if this inequality is a strict inequality at all points except alpha equal to 0 and alpha equal to 1. So the geometric interpretation is that this curve lies strictly below the line segment joining the 2 points. All right. So this is the definition of convexity. How do you test whether a given function is convex or concave? This is something you would have seen in high school. The second derivative test, right? So suppose you have a function f which is twice differentiable. Is convex. If and only if second derivative is non-negative. This is true for functions defined over the reals, only over the real line, not for vector valued functions. Right? What if it's a vector valued function? The Hessian should be positive semi-definite. What does it mean for a matrix to be positive semi-definite? Two equivalent definitions. So let's maybe write that down. So if f from A to R and A is a subset of Rn, f is convex if and only if the Hessian is positive semi-definite, all right, which is equivalent to saying that a vector x transpose Hessian times x is greater than or equal to 0 for all x in Rn. And when I say the square f, I assume that this is evaluated at a point, let's say x prime. Right? Or equivalently, the Hessian, all of the eigenvalues of the Hessian are non-negative. So let's maybe see a couple of commonly used functions and check whether they're convex or not. Let's take something. Let's start with something very simple. X square. Again, it's a function over the reals. What can you say about this function? Is it convex, concave, neither? It's convex, and why is it convex? You take the second derivative, what is that equal to? It's equal to 2 for all x, right? So it's a convex function. Great. Now let's take f of x, where x is a vector, to be equal to the L2 norm of x square. So it's essentially a sum of squares. Yeah? Is this convex? Concave? Okay, it's convex. Why is it convex? I can't just take the partial derivative, say that it's greater than or equal to 0, and that's why it's convex. Yeah, so there are two different ways. We look at both. So one way is, let's compute the Hessian. Right? What is the Hessian of f evaluated at x? So by definition, the ijth entry is dou square f by dou xi dou xj. Varied over all possible I comma j. When I is not equal to j, what is this second order partial derivative equal to? It's equal to 0, because dou f by dou xj would be 2 times xj. And now if you take again the partial derivative with respect to xi, if I is not equal to j, then this is equal to 0. If it's equal to j, then it's equal to 2. Right? So what is the Hessian equal to? It's equal to 2 times the identity. And what are the eigenvalues of this particular matrix? 2, right? There are n eigenvalues. All the eigenvalues are equal to 2. Okay. That's one way to look at it. The other approach, which is slightly more powerful, is the following. Because in this case, it was simple, right? The Hessian was a very simple looking matrix. You could exactly say what the eigenvalues are. But a useful property is the following. So suppose that I have two functions, f1 and f2, which are defined over the same set. And they're both convex. Then alpha f1 plus beta f2 is also convex for alpha beta greater than 0. Why is this true? So assuming it's derivative, but this holds true even if it's not twice differentiable. If it's twice differentiable, then I agree. The second derivative, or the Hessian of alpha f1 plus beta f2, is simply alpha times the second derivative of f1 plus beta times the second derivative of f2, which should also be which is non-negative, right?
Using the definition,
Use the definition and add it.
Yeah, exactly. You can simply use the definition, the basic definition of convexity, So it's just a 2-line exercise to show that this statement is true. Okay? Any questions? Fine. Great. So how is this property useful? Let's go back to that function we had, which is the L2 norm of x square, which is nothing but summation I equal to 1 to n xi square. From the first exercise, we know that xi square is convex, right? And now we have summation I equal to 1 to n xi square. So the sum should also be naturally convex. All right, is that okay? Great. So here's another problem. What about the L2 norm of x? Or let's start with something even more basic. F of x equal to mod x. Yeah, what is this convex or not? Okay, why is it convex? I won't agree with by graph. Visual proofs are not okay.
From the definition, by definition, we can take cases and then
Sure, one way is to take cases and so on, right?
The first order derivative only increases. It never goes. It is never going up.
Does the derivative exist at x equal to 0? It doesn't, right? So this is not differentiable at all points. So you can't use the second derivative test, for example, to say that this is convex. Yeah.
Modulus acts as a norm over the immediate space of R.
Yep.
By using properties of norm, we can prove this one.
So that's another approach. In fact, you can prove for f of x equal to norm x more generally. In fact, any norm. It doesn't necessarily have to be the L2 norm. This is convex, and this follows just from the triangle inequality. So norm of alpha x1 plus 1 minus alpha x2 is less than or equal to norm alpha x1 plus norm 1 minus alpha x2 by the triangle inequality, which is equal to alpha times norm x1 plus 1 minus alpha times norm x2. All right. So you have to be careful. You can't just use the second derivative test to argue that this function is convex or concave. Any questions so far? So a useful property of convex functions is the following. It's called Jensen's inequality. Which says that if f is convex, in fact can be over any convex set, and x is a random variable over the set A, then f of expectation of x is always going to be less than or equal to expectation of f of x. I won't give a full proof of Jensen's inequality, but I'll at least give you an intuitive reason as to why this should be true. Now let's start with discrete random variables, finite random variables. All right. So we saw that according to the definition of convexity, the function is convex if alpha f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha f of x1 plus 1 minus alpha f of x2. All right. What I want you to show, it's not very difficult to show, but what I want you to show is basically if I have x1, x2, x3 up to xk, and I have alpha 1, alpha 2, alpha 3 up to alpha k, then f of summation I equal to 1 to k, alpha I xi is less than or equal to summation I equal to 1 to k, alpha I f of xk, where each alpha I is greater than or equal to 0 and the alpha i's sum to 1. All right. So basically this quantity summation alpha I xi is a convex combination of not 2 points but in general k points. And by definition of convexity, any function, the function of any convex combination should be less than or equal to a convex combination of its evaluations. All right. So once you agree with this particular fact, if you notice carefully, the quantity inside is nothing but an expectation. Right? Each alpha i's corresponds to the probability that xi occurs. Right? So this is essentially expectation of xi, expectation of x. And the right hand side is an expectation of f of x. And that's all there is. Now this holds true for discrete or finite random variables. This also holds true for random variables defined over a countable set, because in the end it's just a matter of taking limits on either side. So as long as the function is reasonably smooth and there are no jumps, right, this holds true. Right? This holds true even for countable random variables. And again, using just a limiting process, this also will hold true for uncountable random variables or continuous random variables. All right. What really helps us, and this is also another exercise in the lecture notes, is that if a function is convex, it necessarily has to be continuous. The function may not be differentiable, but if f is convex, then it must be continuous. If you take any discontinuous function, then it is neither convex nor concave. All right? Think about this a little. This requires a little bit of thought, but it's also geometrically very intuitive. Right? You just take one point a little bit to the left of the discontinuity and a little bit to the right of the discontinuity. You'll see that the straight line joining these 2 points, if you choose the points carefully enough, you'll have points both above the line segment as well as below the line segment. So this function cannot be convex. Right? For example, if you have a discontinuity at some point, if you take a point a little bit to the right and a little bit to the left, and sufficiently close to the discontinuity, then you have the function value both above the line segment as well as below the line segment. And therefore this function cannot be convex. So if a function has to be convex, it should necessarily be continuous. Any questions? All right. All right, some more terminology. Now, I'm sort of it will feel like I'm switching topics a lot in this particular class because I'm not going into detail of any one specific topic. My goal is just to cover the essentials of what we will require later on. So I would encourage you to go through this material a little more carefully. We'll be reusing some of these again and again. So as we go along, it's good to revisit this once in a while so that you're completely comfortable with this. So suppose I'm given a set A, subset of R. We say that A is an upper bound for the set A if A is greater than or equal to X for all X in A. Right? Straightforward, nothing fancy here. And similarly, it's a lower bound if A is less than or equal to X for all X in A. All right. Now we say that A star is equal to the supremum of A if A star is the smallest possible upper bound for A, for the set A. That is, if A star is greater than or equal to X for all X in A. So A star is actually an upper bound, and it's also the smallest possible upper bound. That is, and for any A that is an upper bound for the set A, I have A star to be less than or equal to A. So similarly, I'll define B star to be the infimum of A if B star is a lower bound for A, and for any other lower bound B, B star is greater than or equal to B. So it's the greatest possible lower bound I can have for the set A. Okay, this is a formal definition, but let's see some examples to make this, to understand this particular concept. Suppose I take A to be the closed interval from 0 to 1. What can you say about all possible upper bounds for the set A? So any number that is greater than or equal to 1 is an upper bound for A. And I claim that 1 is the supremum of A. Alright? Because 1 is the smallest possible upper bound you can have for the set A. Similarly, what is the infimum of A? It's equal to 0. Alright? That's great. But what about the set A, which is the open interval from 0 to 1? It's going to be the same. So both sets have the same supremum and the same infimum. What is the maximum of the set A, of the first set A? What is the maximum for the set A2? It's not defined, right? So in the second case, the maximum is not defined, but the supremum and the infimum are both well defined, right? So in both cases, the supremum is equal to 1, the infimum is equal to 0, but in the second case, the maximum and the minimum are not well defined, but the supremum and infimum are. Alright, so that's the reason why we use this supremum and infimum, because even if a set does not have a maximum and a minimum, the supremum and infimum are always well defined. Okay. Great. So one other concept that we'll use, be last, and it will be the last for this particular class, are the limit superior and limit inferior of sequences. Alright, so let's suppose that I'm given a sequence of numbers A1, A2, and so on. The lim sup as n tends to infinity of an is defined as the limit as n tends to infinity supremum k greater than or equal to n of ak, and the lim inf of an is the limit as n tends to infinity the infimum k greater than or equal to n of ak. This may, at present, this may seem like a very weird definition, and you may be wondering why I'm saying this. But again, this is in a similar flavor to what we saw just now. Even though the maximum and the minimum were not well defined, the supremum and infimum are always well defined. So similarly, if you have a sequence which may not converge to a limit, the limit may not be well defined, but the lim sup and the lim inf will always be well defined. All right. To understand that, let's take a concrete example. Let's see the sequence, say ak is minus 1 to the power k. Does this sequence have a limit? It doesn't, right? But let's try to compute the lim sup and the lim inf. Let's fix a particular n. What is supremum k greater than or equal to n ak equal to, for any n, it's equal to plus 1, right? The only values that ak can take are either plus 1 or minus 1. So the supremum is just a finite set. So the supremum is equal to plus 1. And this holds true for all n, right? So if you look at this particular sequence, right, if you look at this particular sequence, supremum k greater than or equal to n ak, this is equal to 1, 1, 1, 1, 1, 1, 1. And therefore, this has a limit as n tends to infinity. The lim sup is equal to, lim sup n tends to infinity, a n, this is equal to plus 1. What is a lim inf? It's equal to minus 1. And this has this one way of interpreting this again geometrically or visually. So suppose you have some sequence of numbers which may possibly be decaying, but then they also oscillate, right, with some particular envelope. Right, so maybe for k equal to 1, it's this value, k equal to 2, it is equal to this value, and so on. So the sequence oscillates, it doesn't really converge to any proper limit. But in this case, the lim sup and lim inf can still be calculated, and the lim sup will essentially correspond to the limit of sort of the upper envelope of the sequence, and the lim inf will correspond to the limit of the lower envelope of the sequence. Alright, so that's the geometric interpretation of the lim sup and the lim inf. So you have two envelopes, one from above and one from below. Both of them will, so the envelope from above is a decreasing sequence, the envelope from below is an increasing sequence, and both of them have well-defined limits, and these limits correspond to the lim sup and the lim inf. Okay. All right. So let's stop here. We'll continue in the next class, where we'll start talking about data compression.